Hi, my name is Marcel. I'm with the Friedrich-Alexander-University, Erlangen-Nürnberg in Germany, and I'm going to present our work, Unearthing the TrustedCore, a critical review on Huawei's trusted execution environment. So as you may know, trusted execution environments are the backbone for many security-critical services that you can find on modern Android devices. And these TE implementations are usually proprietary, and vendors don't reveal much about their inner workings. So in this research, we looked into one of these proprietary trusted execution environments, namely Huawei's TrustedCore. And during the course of this talk, I'm going to share our insights from this analysis with you. So first, we're going to elaborate on the inner workings of selected components, and I'm going to show you the design and implementation flaws that we found in this implementation. So the outline looks like this. First, we're going to cover some background on Android and the usage of TEs. Then we're going to look at the TrustedCore architecture. We're going to examine the loader, the secure loader that is used by TrustedCore. Then we're going to dive into the Android keystore system. And then we're going to look at a memory corruption flaw that we found during the course of this work. And we're going to show you how we managed to exploit this memory corruption. Finally, we're going to conclude by giving you some lessons learned about TEs in general. So what's the trusted execution environment? So basically, it's an isolated execution context that gives you integrity guarantees for the code that is executed within this execution environment, and it gives you confidentiality guarantees about the assets that the code running within the TE uses. Let's say a cryptography key should stay within the TE and should never be exposed to the world outside of the TE. So you can build trusted execution environments using hardware extensions, and three options of this are listed here. The AMD Platform Security Processor, Intel Software Guard extensions, and ARM TrustZone. So since we're dealing with ARM chipsets on mobile phones, mostly, we're going to take a deeper look at ARM TrustZone here. So just a little refresher, modern ARM-based devices have 4 different privilege levels, which are called exception levels. And as you can see here on this image, exception level 0 is the lowest privilege level, and exception level 3 is the highest privilege level. You are probably familiar with the left side here, which is the normal world software stack. And everything that is indicated in these red boxes here belongs to the trusted execution environment. And down here at exception level 3, the secure monitor is the component that is responsible for the transition between the two worlds. So from the non-trusted execution environment into the trusted execution environment and vice versa. Then within the TE, we have a trusted operating system that hosts different trusted applications. And each of these trusted application basically encapsulates a set of security critical functions that you want to protect using the means of a TE. So, and just to give you an impression of what TEs are out there on Android devices, so on Snapdragon chipsets, you'll usually find the Qualcomm Secure Execution Environment, and examples are like Pixel and Nexus devices, for example. Then there's a TE implementation by Trustonic that has been used by Samsung. Samsung has their own implementation now that's called Tigris, and on Huawei devices, like TrustedCore was used until it was superseded by iTrustT, which is running on the newest Huawei devices. And there's some research out there for almost all of these trusted execution environments, but we by far do not know all about them. And yeah, as I said, we're going to look at TrustedCore here in this research and like some selected components of this architecture. Talking about the architecture, now I'm going to give you an overview. So on the left side here of this image, you can see all the logical components that are hosted in the normal world. And on the right, you can see in red the secure world components. So I'm first going to walk you through the normal world components, and then we're going to cover the secure world. So in the user mode, you can find the regular apps that you can download from the Google Play Store, for example. And these apps usually talk to system services that are basically the backend for the Android Framework API that is a big part of Android. And system services that make use of the TEE have to contact this TEE-CD daemon here to authenticate to the kernel module. And this kernel module eventually basically marshals the request that is going to send over to the TEE by using the shared memory infrastructure that it's set up with the secure world. So now in the secure world, we have trusted applications. One of the examples that we're going to cover later is the keymaster trusted application, and there are other trusted applications. And also we have a global task, which basically acts like an init process on Linux, for example, because it's capable of during runtime loading trusted applications and basically spawning a process space in the secure world. Then the TrustedCore kernel in secure world exception level 1 that exposes a system call interface to everything that is running in the user mode. And also it has all the interrupt handlers for interrupts that are arriving from hardware connected to the secure world, like the fingerprint sensor, for example. And then down here in the exception level 3, this is the secure monitor, and Huawei is using the reference implementation, basically a customized version of the reference implementation provided by ARM, the ARM trusted firmware. Okay, now that we have covered this architectural overview, we're going to look into the secure loader and how this global task init process manages to load new trusted applications into the TEE. So, when you look at the file system, you can find some trusted applications there that are encrypted, and they can be loaded into the TEE. And we reverse engineered how global task manages this loading process. So as you can see here, one of these encrypted trusted application consists of 3 major parts. One of them is this encrypted manifest you can see here. Then there's an ELF file signature, and the ELF file the signature is for is down here in this green box, and it is there in an encrypted form. And there are 2 keys available to global tasks during this loading process. This private key in blue here that is used to decrypt the manifest. When this manifest is decrypted, global task has access to this AES key that it can use to decrypt the ELF file here. And now this signature in red here becomes important, that is verified using this public key that is available to global task. And after this signature has been validated, the hashes of this signature and of this ELF file can be compared, and the loading process is complete if everything matches. All right, and in this loading process, so the crucial piece here to protect the confidentiality of these trusted applications ELF files are obviously this private key here that protects the AES key in the manifest. So we were interested in how this key is protected within global task. And we found that global task is using a white box cryptography scheme, and the ciphertext of both keys are basically part of the data segment of global task. And every time a request arrives that makes use of some loading functionality, these keys are decrypted on the fly. So, and obviously, since global task is executed on this ARM chip, we can make use of an emulator like QEMU user mode emulation and basically execute this white box AES implementation ourselves. And this is how we're basically able to execute like a 20-line C program like this one here and decrypt the private keys ourselves. And yeah, this way we managed to decrypt these AES keys that are part of the manifest of each encrypted trusted application. And yeah, eventually this is how we can overcome this code confidentiality. So we analyzed 133 firmware images that were distributed from July 2015 until April 2018. And we found that 119 of these images were using this white box crypto scheme. And we managed to decrypt confidential trusted applications on Huawei models, on Huawei phones that were released in 2016, and also the P20 Lite that was released in 2018. So another interesting insight is that other research has already reported on the trusted computing base size of TrustZone-based TEs. And it seems like they're not really aware of these encrypted trusted applications. So considering these trusted applications, we have found that the reported, so that the actual trusted computing base size is actually 16 times bigger than the one that was reported by previous research. All right, now we've looked at the secure loader. We're gonna move over to the Android keystore system. So just a little intro to how the Android keystore system works. So when an app wants to perform a cryptographic operation, we can see two cryptographic operations here. One of them is generate a key, and the other one is use this key to encrypt some data. So first of all, generate a key. The app contacts the keystore daemon to generate a key with like certain parameters, and the keystore daemon forwards this request to the keymaster trusted application. And this is the part that is running inside of the TE. So the keymaster trusted application generates this key, and then using a key encryption key encrypts this key and puts it into a structure with some metadata. And this encrypted key blob is sent back to the keystore daemon, and the keystore daemon basically manages the access to these key blobs for like multiple applications. And if the application comes back and now wants to perform, let's say, an encryption operation, the keystore daemon uses the encrypted key blob, the data and the operation, and sends it over to the keymaster trusted application. And of course, the keymaster trusted application needs to use its key encryption key again to decrypt the key blob and have the key material ready to use it to perform the requested cryptographic operation. So, and crucial to this design is the protection of this key encryption key. And this is also what makes the Android keystore system bound to the device, because these key blobs here should be only available in plain text inside of the trusted execution environment. And that means this crypto material is bound to the hardware of this device, basically. So we were interested in how this key encryption key is actually protected in this implementation, and we reverse engineered the key blob structure that you can see here on the right. And I want to draw your attention to the HMAC member at the very top here, and the blob member that you can see here at the very bottom. So, and the HMAC, of course, protects the authenticity of the entire key blob, while in this blob member here, you can find the encrypted key material. It's, let's say, the bytes of an actual AES key, for example. And yeah, of course, for the HMAC you need a secret, and to perform this encryption down here you need a secret too. And during our research we have found that both of these secrets, for the HMAC and for this hidden part in the blob member, these secrets are constant. And they're not only constant, they're also right available from the firmware image. You don't even need a device to access them. And this has been the case for not only one device, but for many devices. So again, we looked at 133 firmware images that were distributed from 2015 to 2018, and all of them were using this constant key encryption key scheme. So what's the consequence? Now, like these encrypted key blobs outside of the trusted execution environment can simply be decrypted. So we're able to export protected key material. And furthermore, we can spoof key blobs ourselves. So we can basically generate authentic key blobs. And earlier I said this key encryption key should be bound to the hardware in some way, and here it is not. That basically means that for all services that rely on this hardware binding, this guarantee is simply not given anymore. For example, your full disk encryption that should be bound to the hardware and should only be possible to happen on the device can basically happen anywhere now. And that is like a severe flaw of this system. Okay, let's move on to this memory corruption flaw we found. So also in the keymaster trusted application, we looked at the routine that is responsible for exporting an RSA key pair, and we found a stack-based buffer overflow. And since we're now able, with these two secrets, to craft our own key blobs, we can craft a key blob that contains our exploit payload. So we're able to import the key blob into the trusted application. We're also able to export it from the key blob from the trusted application, which means this way we can trigger the buffer overflow. And since this is all trusted software and running in the trusted execution environment, you would expect that all the state-of-the-art exploit mitigation techniques are there and effective. So we looked at write, never execute, stack canaries, and ASLR. We found that all of them are there, but stack canaries use a constant value, and once this value is known to the attacker, they're obviously ineffective. And we also looked at ASLR, which has a low entropy of just 1 byte, so 256 different addresses that the binary is mapped to, and also a severe flaw. Once the trusted application crashes, it is reloaded to the very same address again, and you basically just need one leak from one of the crashes to basically figure out the entire address space layout. So yeah, these two, like stack canaries and ASLR, are not really effective here. So we managed to use a code reuse attack, simple return-oriented programming on ARM ARH32, and from there we were facing the higher privilege levels, so the trusted operating system and the secure monitor. And for the trusted operating system, we found that there are approximately 174 system calls that are exposed to the user mode, the trusted application we just gained arbitrary code execution in. And one of these system calls is especially useful because it allows us to map physical memory pages to the virtual address space of our trusted application. And we found that all the checks in this system call that should prevent you mapping code pages of higher privileged context into your lower privileged context are ineffective. So you can basically take over the kernel from your user space context, and yeah, that's also a design flaw in itself. So this is how we basically managed to escalate our privileges to the highest level possible on this device. So to conclude, I'm going to give you some lessons learned. So the supposedly hardware protected cryptographic keys. So in my understanding, like ARM TrustZone is more to be understood like a trusted execution environment construction kit. So it highly depends on the hardware and software choices of the system designer, and yeah, depending on these choices, you get certain confidentiality and integrity guarantees. And if you don't have hardware that protects your cryptographic keys, then you're like falling back to software-based security by obscurity designs. So, and these designs, software-based protection, we have seen the severity here once again in history, and basically the leakage of this key encryption key that has been reused on multiple devices over multiple versions of the firmware basically render the device binding of an entire generation of smartphones ineffective and opens the door for brute forcing the key encryption of the device. Lessons learned regarding the attack surface. So we've seen that the trusted computing base is huge, like 16 times huger, 16 times larger than previously reported by other researchers. And the attack surface is wide, meaning everything we have found is part of the user mode in this trusted execution environment and directly exposed to the untrusted normal world. So and all of these components are written in languages like C and C++, which are prone to memory corruption bugs. And you would think that effective mitigations are in place to mitigate the risk of an exploitation, but that is just not the case. So to sum it up, we reviewed Huawei's trusted execution environment. We examined and broke the secure loader and also the Android keystore system. We found and exploited a previously unknown memory corruption bug and were able to escalate our privileges to the highest privilege level possible on this device. And in the end, we shared our lessons learned from our analysis. So that's the end of my talk. Thank you for your attention. I'm here for questions. And if you want to contact me later, this is my email and my Twitter.